This is Steve. He's been smoking cigarettes since he was 25. Now that he's nearing 60, he's beginning to experience shortness of breath and a chronic dry cough. Steve becomes concerned when he becomes too winded to walk upstairs and decides to go to the doctor. When the doctor listens to Steve's chest, he hears crackling sounds like Velcro. He measures Steve's oxygen levels to find that they are hovering below 95%. The doctor tells Steve that smoking has likely caused long-term inflammation, leading to progressive damage and scarring of his lung tissue. This scarring, called fibrosis, prevents enough oxygen from being taken up into the bloodstream. He explains to Steve that current therapies for this disease can slow progression or manage symptoms, but that only 20% of fibrosis patients live for 5 years following diagnosis, even with treatment. The only true solution for late-stage fibrosis is a lung transplant. Scientists are working hard to find ways to reverse chronic lung inflammation like Steve's. Using mouse models, researchers recently observed that the lungs of mice with induced pulmonary fibrosis have a lot of extra macrophages hanging out in their alveoli. Macrophages are basically the coolest cells. Their job is to destroy potential threats, such as bacteria and debris, by engulfing and ingesting them. But right now, they are overstaying their welcome, thanks to genetic signaling that allows the macrophages to avoid programmed cell death. Scientists have developed new promising therapies intended to reverse inflammation at the genetic level. The problem is that these drugs aren't useful right now. The body recognizes them as foreign and destroys them. How can we solve this problem? Well, it turns out that all they need is a little protection. Let's put the drug inside polymeric microparticles and try again. Not just any microparticles, though. They have to be biocompatible, uniform in size, and degradable, and they need to be able to carry a payload, such as a drug. They also have to be taken up by the macrophages, so they are synthesized to be about the same size as bacteria. This time, when the drug is inhaled, it is surrounded by a polymer and protected from the body's defenses. The macrophage gobbles it up and holds it in an acidic pocket where the microparticle breaks down. The therapy can then be released to the nucleus and used by the cell. In this context, genetic therapies typically work by silencing genes that have been associated with lung inflammation and fibrosis. Mouse models have even shown reversal of fibrosis after gene silencing. Utilizing a protective delivery method like polymeric microparticles will allow researchers to create genetic drugs that may one day reverse fibrosis. This is very good news for people like Steve.